Okay, so I'm going to talk about what we can learn about gravitational waves with about black holes. So first of all, as I'm sure you're aware, there has been direct detection of gravitational waves, at first by these two LIGO detectors, and later on joined by the Virgo detector in Italy. And there's more detectors under construction, for instance, in Japan and also in India early in the next decade. Now, an important thing about these detectors is that, yes, we are now at the state with the instrumentation that gravitational waves can actually be observed, but we are not yet at the stage where we can learn something useful about compact objects. However, this is only a few years in the future. So basically what you should imagine is what has happened actually in the past 10 years as well, is that detectors are upgraded, then as a test almost, an observing run is done, and hopefully things are seen, of course. Then detectors go down for an upgrade again, as is the case now, and so on, until the design sensitivity is reached and the facilities have reached their capabilities. So then, this is the prime source for gravitational waves, as we have already observed these. So in a cartoon picture, what happens is, let's assume you have two black holes, but could also be two neutron stars. They spiral towards each other. They lose because they lose orbital energy in gravitational waves. Another thing that gravitational waves will take away from the system is orbital angular momentum, so the orbits will circularize. And by the time the motion has, and therefore the gravitational waves have sufficiently high frequency to be in the frequency band of ground-based detectors, you have quasi-circular in-spiral. And this ends at some last stable orbit, at which point the two black holes will plunge towards each other and merge to form a very highly excited black hole. And actually much of this talk will be about this phase, whereas what we've observed so far is actually mostly the in-spiral and the merger. Here you have a cartoon picture of the shape of the gravitational wave that comes out. So during the in-spiral, you have the frequency steadily increasing, as you can visually see. You have this peak, which is more or less the merger. And this is the ringing down of that black hole, that single black hole that is formed and is moving towards a quiescent state. Now, the first detection, I think you will have seen a plot like this before. Here you have the raw data from the two LIGO detectors, which actually looks uncannily like this basic shape that I showed here, except that there is detector noise mixed in, and that is why it looks wiggly and ugly and so forth. Now, to dig out the actual shape of the signal, you can do a variety of things. So one obvious thing you can do is you could take analytic predictions for these shapes. You have a family of waveforms, waveform models, so waveform model that you trust, and different members of that family will correspond to different choices of the masses of the two black holes and the spins of the two black holes. And you can pick waveforms with different masses and different spins and check which one matches the data best. And that is here depicted in dark gray. On top of that, in red, is the result of a very large-scale numerical simulation with the same masses and spins that yielded the best fitting analytical waveform. And that's something that you can't very well see, but that's actually a good thing. The light gray here is a method for reconstructing the signal that uses no information whatsoever from general relativity. And the fact that you can hardly see it means that it is closely following the analytical templates. And that is, again, something that will become important later. Having the ability to observe merging black holes, and by now also neutron stars, gave us our first direct access to the generally strong field dynamics of space-time. This plot here illustrates how dramatic this is. So on the x-axis, you have some characteristic time scale of some process or other. And so very dynamical corresponds to the far left, of course. And on the y-axis, you have a measure of the curvature of space-time. The solar system lives here and is rather boring in that respect. Until now, the most general relativistic object was a binary pulsar, so two neutron stars that were observed by radio astronomers, which, however, are very far from merging. So that is moderate time scales and actually moderate, weak space-time curvatures. And the events we are seeing now live all the way up here, and that is what you need to really put at least classical general relativity to the test. So that has been done. So now we have, I could fill another slide with references to papers that test the genuinely strong field dynamics of space-time, and in fact vacuum space-time as far as we know. Also you can do tests of how gravitational waves propagate over large distances by looking for any evidence of dispersion, which led to an upper limit on the mass of the graviton of 10 to the minus 22 electron volts, and so on. But now we want to make the next step. And the next step is to look at the very nature of the two objects themselves. So when we see two very massive objects merging, we tend to say, oh, they must have been black holes, but how sure are we really? So how certain are we that the objects we're observing are in particular the standard black holes of classical general relativity? So in the literature you'll find motivation for a host of other possibilities: boson stars, which are condensates of some bosonic field; dark matter stars. So dark matter, if it consists of fermionic particles, you can imagine them congregating into star-like objects held up by degeneracy pressure. Gravastars have an ADS core and are surrounded by an ordinary shell of ordinary matter to keep them together. Wormholes are even more exotic, I guess. Then prompted by Hawking's information paradox in string theory, there have been these ideas of firewalls and fuzzballs, and there may be unknown types of objects lurking out there, even that nobody has ever envisaged. So how do we search for evidence that what we are seeing could be any of those possibilities? How can we tell the difference? So I think the most exciting avenues, at least to me, but there are others, by the way, is two possibilities, and those will be the focus of the rest of the talk. So one possibility is by looking at the ring down of this newly formed compact objects formed out of the merger of two objects. This ring down, this violent shaking as the object goes towards a quiescent state, can actually be used as an indirect test of the black hole no-hair conjecture. And alternative objects, for instance, in the case of boson stars, you'll have, if you look at characteristic frequencies or damping times in the ring down spectrum, they can differ from black hole ones very significantly by factors of several. And another way, perhaps more speculative, is searching for so-called gravitational wave echoes. And I'll come to those. So first, ring down and an indirect test of the no-hair conjecture. So very, very crudely, assuming that the Einstein-Maxwell equations for classical gravity and electromagnetism, then a stationary black hole is completely characterized by its mass, its spin, and its electric charge. Astrophysical black holes are not assumed to have an electric charge, so I'm going to drop that for the time being, and we just say that stationary black holes are characterized by their mass and their spin. And so now, how are we going to probe that with gravitational waves? Because this is a statement about stationary black holes, which almost by definition, they don't vibrate, they don't emit gravitational radiation. Well, if you look at the ring down, so this ring down, at least at the late stage, basically can be described as a Kerr metric plus some small, therefore linear perturbations. And the ring down gravitational wave signal is then a superposition of what we call quasi-normal modes, which are damped sinusoids with some characteristic frequencies in here and characteristic damping times. Now, how is that related to the no-hair conjecture? Again, no-hair conjecture says that stationary electrically neutral black holes are completely characterized by mass and spin. Now, the point here is that if you look at the linearized Einstein equations around a Kerr background, then what they enforce is that all these characteristic frequencies and all these damping times can depend on only two numbers, namely the mass and the spin of the final black hole that the system is asymptoting towards. And so in that sense, if you could check those relationships empirically, you would have an indirect test of the no-hair theorem. We looked, in the case of the first detection, GW150914, we actually looked, since it was a particularly loud one, still the loudest binary black hole merger that we've seen so far, we did look for evidence of a least damped quasi-normal mode by trying to fit a single damped sinusoid to the data, and we got something that is consistent with the in-spiral regime that comes beforehand. You see the two masses and the spins of the in-spiraling black holes together with general relativity will give you a prediction for what should be the frequency and the damping time of the least damped and therefore most visible mode. I'm not going to explain this very busy plot here, but that is all we were able to do. We were not able to pull apart the intricate structure of the ring down. For that you need something that, the same event actually, but 3 times louder as seen in the detector. That means we need a factor of 3 increase in the sensitivity of the detectors. And this, well, if everything goes well, of course, with upgrades, this will actually happen by 2021. So that is what I'm writing here. So 15914 would have been 3 times louder in advanced LIGO Virgo at the final design sensitivity. So how would you test the no-hair conjecture? Well, you do a measurement whereby, it's very simple, you just do a measurement whereby, this is the relationship, the GR predicted relationship for standard black holes between these frequencies and damping times on the one hand, mass and spin on the other hand, and you allow for some relative deviation. And so if the no-hair conjecture is valid and you are dealing with a standard black hole, then these deviations should be 0, and so your measurement should be consistent with 0 within the uncertainties. For that you need a very good ring-down model, and we have that by now. I'm not going to go into details here. Let's just assume that the theory is under control in the case, again, of standard black hole in general relativity, and then we're going to look for deviations thereof. So what you find is if you do these measurement of these relative deviations, which you have to measure along with all other parameters in the problem, right? So the final mass and the final spin, not only that, but also the sky position, because everything is, all the parameters you can measure are correlated with each other. Nevertheless, what you find is that with advanced LIGO Virgo at design sensitivity, also, by the way, you can combine information from multiple sources, and then the quality of your measurement will improve with the square root, roughly, of the number of detections you make. Already with 6 sources, similar in loudness and mass, similar to the first detection, but now, again, with the detectors at final design sensitivity, you can measure possible deviations in the frequency of the 220 mode down to 2% accuracy, and the damping time down to 10% accuracy. Then gravitational wave echoes. So that is more speculative. Ring down we really expect to see, and we then we'll see whether these frequencies and damping times are as we expect. But gravitational wave echoes is different. So here the idea is you have some exotic object, which may not be a black hole, and basically, this is in the case of a black hole. If you look at the potential that governs radial motion, you'll have a bump here corresponding to the photon sphere. Now, if you have an object that is compact enough that the photon sphere sticks out, but it's inside, it doesn't involve a horizon, then there can be a second potential bump on the inside. Now, if such an object gets formed, for instance, from the merger of 2 other objects, then, well, some of the gravitational radiation will go to infinity and can hit a detector. The ingoing gravitational waves, which there always will be, normally would get lost because they would disappear behind the horizon and would never reach a detector anymore. But what can happen in this situation is that ingoing waves bounce back and forth between those 2 potential barriers, and at each reflection here, some of it can trickle out in the form of these bursts, and these are called gravitational wave echoes. So you can have a situation whereby there is a ring down, but then even after the ring down has died down, you have these bursts of radiation coming out. And you can show that it will be generically the case that if you have some microscopic horizon modification, or there's some small length scale associated with this potential here, then, pardon me, then the time between successive echoes will be more or less constant. It will be proportional to the mass of the object times the log of the mass of the object again, divided by this length scale. I'm setting g equals c equals 1, of course. And then there's a prefactor n, which depends on the nature of the object. So for wormholes, n equals 8. for thin shell gravastar 6 and 4 for empty shells and so on. And then one can do a simple exercise. You take the mass, 65 solar masses associated with the remnant of our first detection. Hopefully this will come up, yeah. So you take a mass of 65 solar masses, reasonable astrophysical number. You take this horizon modification to be the Planck scale, and for definiteness n equals 4, you get delta t of 117 milliseconds. This is good for us because, first of all, the ring down for an object with this mass will last in the order of 3 milliseconds. This is longer than that, and so the first and probably loudest echoes coming out will be well distinguished in time from the ring down. On the other hand, this number could have been 1,000,000 years, in which case no data analysis method would have been needed because there would be no possibility of seeing anything. Now, an important point is that so on the one hand, the calculations for the shapes of echoes that have been done so far for relatively concrete types of objects like these here, you should consider them straw man objects in a sense, but also even then the calculations that have been done are perturbative. They are not sufficiently reliable that you would use the output to start filtering or matching, trying to match these waveforms against the data. But a larger point is that again there could well be objects that do emit echoes but have yet to be envisaged and are of a completely unknown nature therefore. And so what we want is to look for echoes without making any assumptions. So look for echoes in a morphology independent way. Now, for this, there already existed algorithms. One is called Bayes wave, which depends on a decomposition of a signal in terms of what is complicatedly called Morley-Gabor wavelets. They are just signed Gaussians, so what you see here, and they come with a number of parameters characterizing them. And that was actually the decomposition that was used for this assumption-free reconstruction of the in-spiral merger ring-down signal of GW150914. But now you might ask, well, how was this done? Because, of course, you can, these guys form an overcomplete basis in some appropriate signal space. So, if you take the raw detector output, then you'll be able to fit all of it, including the noise. How do you dig out the signal and reconstruct that so nicely? Well, here I don't have time to go into much detail, but I can give you a flavor. Basically, the output of a network of gravitational wave detectors can be written like so. So you have some response function responding to an astrophysical signal. Then there is the possibility of instrumental glitches, which means there is power in the output of one detector, but not necessarily the other one, because this is not something of astrophysical origin. And then there is normal detector noise, meaning stationary Gaussian noise, if you want to be technical. Now, you can consider three hypotheses. One is the signal hypothesis, which says that the data contains a signal and normal detector noise, but not glitches. So then the middle term would not be there. You just have the detector responding to a signal and then ordinary detector noise. There is the glitch hypothesis, which says the first term is absent. And you have some glitch in one or more detectors at the same time can happen, plus ordinary detector noise. And then the noise hypothesis, which of course says you just have ordinary detector noise. Now, in a Bayesian framework, it is possible to compute ratios of evidences for instance, the signal hypothesis versus the noise hypothesis, or the signal hypothesis versus the glitch hypothesis, whereby these probabilities here can be computed using some prescription. Again, I can't go into detail here, but they do involve wavelet decompositions, both for the signal hypothesis and the glitch hypothesis. And now the crux of the matter is, suppose that a signal is actually present. Well, a signal is something that has to be coherent between multiple detectors, unlike a glitch, which is not consistent between detectors because it is tied to one particular detector. And now the Bayesian formalism, Bayesian statistics, has an inbuilt version of Occam's razor, and so that leads to the fact that if a signal is present, then the signal hypothesis tends to be preferred, because to describe a signal, to characterize the signal, you need a smaller, or the signal needs a smaller number of degrees of freedom than a glitch. And that is because, again, a signal needs to be consistent across detectors. And then suppose that it is the case that you find a lot of evidence for a signal being there, then the wavelet decomposition associated with that signal hypothesis provides the signal reconstruction of which this light gray here was an example. But now we want to go to echoes. And so instead of, we want to help ourselves, right? So instead of just decomposing into ordinary sine Gaussian wavelets, which we could also do, by the way, what we will do is generalize our wavelet to a comb of sine Gaussians. So each blip here is a sine Gaussian in its own. There's some characteristic time difference between them, delta t, some phase shift, doesn't matter now, some damping factor in going from one sine Gaussian to the next, and a widening, which is also typically seen in echoes as they come out of calculations, of course. That means we're still not assuming much about the behavior of the signal, which would be wrong, because a real echo signal isn't going to have this form, and therefore will not have, in particular, a well-defined damping factor or a well-defined widening factor. In fact, the best you can hope for is the fact that delta t, time between echoes, is constant, because that at least seems to be universal. But it doesn't matter, because we're still doing a decomposition into wavelets, and that is the point. And so how well does that work? Well, we can use some toy model prediction. So this is a waveform that you get if you assume that you have a Schwarzschild spacetime with Neumann reflective boundary conditions just outside where the horizon would have been, and you have a particle that spirals into it that has 1,000 times less mass, so it's almost a test particle. You look at the waveform gravitational radiation that comes out. So this is the in-spiral, particle gets absorbed, and then echoes come out. Again, this is a straw man. This is just to test the algorithm. And of course, you can use many qualitatively different types of echoing objects. But something that will generically happen is the following. So first of all, important, even if you know you only have noise, it can be that ratios of evidences will somehow prefer the signal over noise or the signal over glitch as a statistical accident. And that is something you have to quantify. This is not a small point. So these histograms here is what you get for the ratio of evidences, or log actually, of signal versus noise and signal versus glitch. So these distributions is what you get from just noise. And it had better be the case that if you're going to claim, say, a 5 sigma or more detection of echoes, then it had better be the case that when you measure right after in-spiral merger ring-down signal, that the detection statistic, let's call it, goes above that background. And this happens for, this is, would take more time to explain, but for a signal-to-noise ratio of 12, a loudness in echoes of 12. Now, what is the significance of that number? Well, that's comparable to the loudness that a ring down, again, of GW150914 would have had for if it had been seen in detector upgrades in immediate future. And why is ring down significant? Because we're talking about echoes here. Well, my assumption is that the total power in all echoes combined will be of the same order of magnitude as the power that was in the ring down. So that means that in the rather near future, if echoes exist, we should be able to find them. And of course, these plots are based on this simple toy model example that I showed on the previous slide, but there's good reason to believe that these sort of statements hold generically. And just for completeness, here is the wavelet reconstruction of the echoes from the signal that I showed earlier. The light gray is signal plus noise, so it is impossible by eye to see anything in that. And then the maroon is the signal itself, and the orange is the reconstructed signal. So in summary, so what we've done before, and the results papers exist actually, is look at the generally strong field dynamics of two objects spiraling around each other and eventually merging. We assume that this is a vacuum process. This is very neat physics, very crisp. But what about the objects themselves? Are we really so sure they are black holes? And so in the very near future, we will be able to look at that by probing the ring down, which will enable an indirect test of the no-hair theorem. That is less speculative, and then maybe more speculative, the search for echoes. And so the one thing I want you to carry home is that This is not measurements we're going to do 100 years from now. These are measurements we'll do in the next 2 years. Thank you.
Okay, thank you very much. Is there any questions right now? Yeah, I see you.
I thought there was a claim actually of a detection.
Yes, there is.
Can you say something about that?
Yeah, I left it out of these slides because it's a longer story. If you're interested in the details, we can talk over coffee. But there's the statistical method used is not quite sound, in the opinion of not just me, but also members of the LIGO Virgo collaboration who have also looked at this.
Okay, I suggest that we thank Chris once more again for this nice presentation. And then there will be a half-hour coffee break.